So Helge asked me to give this kind of talk, and this is, I don't know, it's a very difficult talk for me because I think my goal is in this first talk is supposed to tell you kind of what does it mean to prove homological mirror symmetry. What does the statement mean? How can we hope to prove something like this? And it's such a technical subject that kind of every time I try to resolve some of my confusions, I spend one day that never ends. So let's see how it goes. Okay, so if please just interrupt me. Let's kind of try to make this useful.
Okay. Do you still have 10 minutes at the end of your talk to Bernd?
He didn't want it. I didn't want it. I opened. Okay, so let's start with M omega. This is a closed symplectic manifold. And I will restrict to the Calabi-Yau case, which, so I will not only restrict to the Calabi-Yau case, I will also fix a holomorphic volume form, but I will do both of these in the symplectic world, so it's much more flexible. So I will assume that I have, well, let's do this one, but we can just say C1 of m equals to 0. But also with trivialization of the bundle that this is the obstruction to having a section of, so I will include a section with the trivialization of the top. So that, let me just write it. Okay, so this is some homotopy. Okay, so this is some flexible version of a quadratic volume form.
What is the substrate on the?
It's just top C. It's exterior.
Do you need to pick an almost complex structure?
Yes, I need to pick an almost complex structure. So this is kind of, so let me just write J. So you make some choice of a compatible almost complex structure that turns this into a complex vector bundle, and then you take its top exterior power and then take it. So we can forget about this if you want. So this is like the canonical bundle, and it's independent. If you change this almost complex structure that's compatible with omega, you obtain canonically isomorphic vector bundles. Well, canonically, again, up to homotopy. So all of these choices are made up to homotopy. Okay, so if a trivialization differs from another by kind of a family of trivializations, then they're the same trivialization. Okay, so this is the kind of symplectic choice of a holomorphic volume form. And it will be used to grade our algebraic invariants with Z gradings. Okay, so we fix that. Now what we want to write is that out of this, we should obtain, oh, actually, let me give one more definition. I need more definition before starting. We also need to introduce a Novikov field, and I will work with kind of the simplest possible Novikov field. This is K, R. This here K is characteristic 0 for safety. You can take it to be complex numbers. So these are sums A, I, to alpha I with AI and K, alpha I real, and alpha I goes to infinity as I goes to infinity. maybe let's make this zero. Okay, so this is the Novikov field with one parameter and real exponents. Okay. So now I can at least say what we're supposed to have. So this Fukaya category of M is supposed to be a curved A infinity category over this Novikov field.
Okay. So supposed to be means this is part of the conjecture, or what does it mean?
Let me continue. Okay. So whether this thing really exists or not is a. I mean, it definitely exists, but is it in the literature? Like with exactly what generality it's in the literature? I'll try to say what I know. So okay, but let me first say what is objects are supposed to be. So they are graded. So this grading, let me not actually get into this, but it's some data like this, but you have to fix it on every Lagrangian to make them graded. It's a real choice. If you have a special Lagrangian that has a canonical grading, for example. Graded, oriented, spin, Lagrangian submanifolds. Okay, so this oriented and spin, I'm also so I could remove those if I was working in characteristic 2, but in mirror symmetry we want to work over characteristic 0, so I need to choose further data and make further assumptions to be able to work over a characteristic 0 field, which means that I need to assign plus or minus 1 to each of my counts. So I need to orient moduli spaces. And that assumption is used to orient moduli spaces. Again, for example, like this orienting this moduli spaces, this could be a talk in itself. It's difficult. And the literature is also not super well organized. But I mean, it's there if you really want to learn the.
So no local system, something.
Well, okay, so I will kind of have the local systems by having bounding cochains. But you could have that, yes. Could also allow immersed. It's sometimes. Okay, so I feel like that's a direction that I don't want. Like this already is a huge thing. I don't want to make it more huge, but you could. Okay, so now the picture. So now let me here make a remark. So as far as I know, this category, maybe let me not say this category, and it's only rigorously defined after fixing a finite number of transversely pairwise transversely intersecting Lagrangians as objects. So we expect that there is a category with all Lagrangians as objects, but I think maybe someone can correct me if I'm saying something wrong. There is this FO cube and then Fukaya. I think it's actually Fukaya who really defines this. They fix a finite number of Lagrangians and just restrict the objects to be those Lagrangians, sort of all Lagrangians. And these Lagrangians are already transverse to begin with. So this really should be just a technical thing. And if someone really wants to resolve this, they should be able to resolve it. So this is not that serious.
And all these multiply cover controversy is resolved nowadays? So the
So if I answer that question with a lot of confidence, I think you shouldn't believe me. I don't think a single person can know this.
Okay. Please, ongoing.
I'm not worried, but I also don't know everything.
I see.
So, yeah.
So, I don't know more about this subject, but with that, you don't like the approach by Perutz and Sherry?
So I'll come to that. So that's not this, right? That's a different
No.
setup.
Yeah.
So I'll come to that, and that's a good technical fix to these problems that we're talking about. Okay, so now I'm going to pretend that I'm in this case. Okay. I have a fixed number. I have fixed some Lagrangians, any number of them.
Assume that M contains only finitely many Lagrangians, or you just
No,
take
no,
a
just
subcategory
fix.
generated by.
So if there was a category, then you would take the subcategory. But since there is no category, we're defining the only category that exists is the category of those finitely many objects. But then you could, of course, take some kind of limit over adding more Lagrangians and so on. The fixes that you can do.
Okay. So in principle, there might be some more Lagrangians lying around, but you don't consider them. Okay.
Yeah.
The point is you want transverse intersections.
Yes. So the point is that now I come to morphisms. So these morphisms are supposed to be like this. So I will get C as well. Let me write home. Home. Book. And one Lagrangian. Another is supposed to be, so it's good to split this into two parts. So if if the two Lagrangians are the same, then of course it's not really transverse, but it's clean intersection. So we can deal with this. So up here, L, if L equals L1 equals L2, maybe L1 equals L, and so it's just a homology. A chain complex. You can take any. You can take the Ram complex or a Morse. You can fix a Morse function and take the Morse complex. Okay, I don't want to specify this model. Okay, and otherwise, it's this Floer homology between L1 and L2. And remember that these are assumed to be transverse. And in this case, this thing is defined to be a direct sum over all intersections. I just have a copy like this, and the copy P. So I have two Lagrangians. No. Then it's a vector space generated by all of these finitely many intersection points. It's finite dimension.
What means this symbol?
Which one?
P,
The spanner, like just the
the previous one?
lambda. So it's the numerical field.
Okay.
This particular field with a formal parameter. And this formal parameter will keep track of areas. So I didn't tell you. So this is just a vector space now. And then I have to equip this with this algebraic structure. Okay, and this is what's called the curve the infinity category. Okay, let me try to say that. Okay, and then structure maps. These structure maps are a sequence maps like this. Okay, so mu0 is an element of this home. Let me start omitting the there's only one category so far, Hom L, Hom L. So for every Lagrangian, I have an element of this vector space. Okay? And this element is roughly obtained by counting disks, Maslow zero disks with boundary on my Lagrangian. Okay, roughly.
Say it again.
Huh?
Say it again.
I have a Lagrangian. So I fix the J, and then I'm looking at holomorphic maps, J holomorphic maps from a disk to the manifold with boundary on the Lagrangian. And that's going to be a finite count. And it will give me an element of this linear span of these intersection points. If you do this right. So sorry. So let me correct this. No, that's not. I said this wrong because I'm trying to. But it's better to do it here in this model. Sorry, I think that was confusing. So you have to count kind of where the marked point goes, and then that's going to span a cycle, and you're going to record that cycle. Okay, so omega 1 is what's supposed to be the differential of these graded vector spaces. Also, these are graded. Sorry, so it's graded. That's also graded. So it's one, two. Oh, and this is a degree 2 element. Also, okay. So let's do it like this. 2, and this one increases degree by 1. So this is supposed to be in good cases where you don't have this mu0 term, you don't have these disks with boundary on the Lagrangian. This guy is a differential. So mu1 squared, then you write the relationship that this satisfies it, something like mu0. How do I do it? Mu2 inside mu0, this, and plus minus, but it doesn't cancel. Mu2, mu0, like this. Okay, so this square of the chain, this thing is a square of this mu1, the thing that's supposed to be a differential of the chain complex, is actually not 0, but it's given by commutator with this curvature element. And this doesn't have to be 0. So in the early days of Floer theory, you would always work under assumptions where this mu0 is 0, so that this is a chain complex, and then you would take its homology and prove things with this homology. But in mirror symmetry, this reduces generality by too much. You can't do that. Okay, and then we have, let me write so let's put this parentheses. So I mean, I said something confusing because there is a way to define this mu0 by first perturbing and then counting there. So that's also possible. But it's better to do to use this model and then use the evaluation maps. Okay. Okay, and this one is supposed to be a product. L1, L2. Okay, now there's the endless discussions about how I should write, which order I should write these things, but I will not be careful. I'll write it like this. L1, L3. Okay, so it's just exactly the structure of a composition in a category. Okay? But why is it not exactly the structure of a composition in a category? Because it's not associative. Again, I can write something like this, where on this side, I have the relation that if it was associative, this side would be 0. And on this side, I have something that contains mu0, which is not always 0. Okay? So therefore, well, not just mu0, also mu1. So this associativity, sorry, okay, again, let me backtrack. So this non-associativity actually is not related to mu0. Even without mu0, you have this non-associativity. I don't know. Is this clear? Yes? So 0, mu1, and this one preserves degrees. So this one is degree 2, degree 1, degree 0. It goes like this, 2 minus d, where d is the number of inputs. And there is, so these things satisfy infinity relations. They satisfy infinity relations, which are quadratic in these, so it looks something like this. So mu j, and then you have a number of inputs that you're just gonna fill, and then you have this mu k here, and okay, and again a number of slots that are empty. Okay, and this one inside has some empty slots. Let me indicate that. Okay, and this is a sum over all j plus k equals, let's say, n. Okay, so I get a relation for every n. Every n equal to 0. Okay, and this is supposed to be equal to 0. And there are signs. Okay, so this what I wrote here is the case where n equals 2. And for n equals 1, you get that the curvature term is closed. So when you apply mu1 to it, you get 0. That also doesn't cancel, I think. So you usually get a closed element. And if you, so this one, you have to look at n equals 3. N equals 3 tells you, well, n equals 4. What do I get for n equals, for n equals 3? I will get something about the Leibniz rule. So the Leibniz rule will also not be satisfied on the node. For n equals 4, I will get this associativity relation. So that comes from like, the associativity is just like, you have mu2 here, and you can place the mu2 here or here. And if there was nothing else, that would just tell me that it's associative. But I have mu0 and mu1, so there's many other terms. It's really not satisfied. Okay? Any questions about this?
So have you used so far the condition on the finite number of Lagrangians at some point or not?
So that's related to how, for example, how will you define the differential? You will define the differential by taking like an infinite strip like this, okay? And okay, so let me do it. So let's say I'm trying to, let's say this is P, this is Q. I'm trying to compute mu1 P, and I'm trying to compute the coefficient of the Q coefficient of mu1 P. Okay, so I will do that by counting solutions of maps from this infinite strip into here, such that when I go like this, it will converge here. When I go like this, it will converge here. And there's a J holomorphic, there's a almost complex structure. The map is supposed to be J holomorphic. And this side is supposed to map. So this, let me call this one L1, L2. So this is supposed to map to L1. This is supposed to map to L2. Okay. So now I need to be able to set up the analysis that will allow me to count these things and then prove that these relations are satisfied. So that requires this problem to be, when you linearize it, at the solution to be a Fredholm problem. And this transversality is used to prove this transversality. It's some kind of Atiyah-Potodi-Singer index problem.
So there are no theorems that tell you that you can perturb. So that,
there are theorems that you can perturb, but if you really think about it, you'll see that it's not. It's just a bookkeeping problem. You're supposed to choose all of these perturbations simultaneously. So it's not, as I said, it's not the deepest kind of most important issue that we have. It can be solved.
But it has not been solved so far.
But it's like you should already be super happy if you can compute it for any collection of finite Lagrangians. So it's not like this is enough.
Okay, and there are some things that if you add some Lagrangians at some point,
Yeah, you can perturb
change the Fukaya category. So you have some.
Yeah, so that's a good point. So you would really like to have finite many Lagrangians that capture everything.
Yeah, and this is a thing.
This is a thing, yes.
Okay.
This is but it's not a general theorem at all. But it's in mirror symmetry situations. This usually happens.
Usually happens.
Well, okay.
I mean,
Sometimes happens. I don't know. Let me see.
countable infinity should be fine, right? Countable infinity.
Yeah, countables.
That works.
I know how to do it.
with the
Very
transversal,
uncountable. I claim that.
once you have
so-
families of Lagrangians, and then you're stuck, I guess, right? With traditional. I mean, then we don't know how to do a transversality.
I claim that I know how to do it, but, but I didn't write it, so I don't want. I didn't.
But
wanna
not
say it.
with the kind of perturbation. I mean, like.
No, you kind of keep you kind of perturb it in all possible ways, and then take a limit over that.
But if the Lagrangians don't intersect transversely, that
Yeah.
that's
So
the
you
work-
look at all ways
I
of
see.
perturbing that.
You perturb the Lagrangians.
Yes,
Sure.
yes,
Yeah.
yes.
That works too.
Yes.
So for some reason you don't want to do the isotopy thing. Isotopy.
But it's like for every problem, will you do a different?
No, that's what he said. That's a perturbation of the Lagrangian. With Hamiltonian isotope.
Yeah, that's a standard way to do it.
Yeah.
Yeah,
but
What's
you need
the
to
standard?
bookkeep.
God,
You need to
come on.
bookkeep.
I'm talking about what's in the literature. Okay, everybody. I heard like every single person claim that this is easy. It's not in the literature,
No,
so I don't want to add to this. There are methods, there are techniques. I don't think there's anything written in this full generality that says that construct this category with more than finitely many already transverse Lagrangians. And I don't claim that this is a serious problem. I think that's enough to say. Okay.
So, Umut,
Yes.
you mentioned that this is sort of hard to compute. Is it, and that you will talk about techniques to compute it? Is there like any simple example where it is computable, or is that the wrong?
Yeah,
question to ask?
so I think the main excitement about mirror symmetry for symplectic geometry was that you can compute it sometimes. Like it's this, like I think before mirror symmetry, even for like elliptic curve or something like this, I'm not sure if people really computed it before. But you can compute it. Mirror symmetry holds, so that's why. Like it's for this purpose, mirror symmetry really is used for something else. It's really used to compute this category.
I made a statement that conjecturally should hold in a certain situation with the L and phi k L.
Right.
That would have some relation to this intrinsic measure.
Okay, so now this guy, this category, this Fuk M is curved, and we don't like working with curved infinity categories. Their algebraic properties are not so nice. But actually, there's a meaningful way to go from a curved infinity category to an uncurved infinity category by considering what's called these bounding cochains. So by these bounding cochains, you kind of add, add a term to your differential so that the differential now squares to 0. And there's a systematic way of doing this so that all the relations are satisfied. Okay, so let me just say that we can construct an uncurved usual. So uncurved means this mu0 is 0. So uncurved means 0. And then, for example, the morphism spaces are chain complexes, and you can take their homology. So homological algebra works. Uncurved infinity category that I will call Fuk BC for bounding cochain M. And again, if I'm trying to stick to what's in the literature, I should fix these Lagrangians. Okay? But again, I don't think this is an issue. I think you can have all Lagrangians. Okay. Okay, and whose objects are the objects of hook N, same objects, but equipped with the extra data of a bounding cochain. Okay, and I don't have time to really define what this means, but let me comment that not every Lagrangian admits even a single bounding cochain. So there are Lagrangians, in fact, many Lagrangians, that just do not admit a bounding cochain, and they just don't end up being an actual object of this Fuk BC. So this is the category that we will eventually compute. And this category will not say something about a Lagrangian that does not bound this, that does not have one of these bounding cochains.
It's an element in some form.
Some, yeah, usually in the first degree. So let me just write. So it's an element in Hom 1 LL. And these are some kind of, okay, solutions of Morikawa equation, and may not exist at all.
Just like a tangent vector to the
I mean, so they satisfy this equation. Let me just write the equation. So mu I b equals 0. There's a sign, but this starts from 0. It's just like the usual Morikawa equation. If you didn't have a mu 0 and the higher mu 3, mu 4, and so on. If you just had mu 1 and mu 2, this is the usual Morikawa equation.
So does that mean that you can use it to deform the infinity structure?
It means that you can use it to, so for example, if you have L1, B1, and L2, B2, now you can modify the differential, but the mu1 of the original category, so that this actually is there is actually a differential here. So you fix a bounding cochain on one, a bounding cochain on the other, and now there is a way of actually defining a differential, starting from the data of the existing mu1, and then using also this extra data, mu1 and mu2.
But I think what Helge said at the answer, yes, right? So these solutions to the
But I'm doing something more than that. I don't have any infinity category
yeah,
yet.
let me finish what I want to say. So the B gives you a deformation of the infinity structure. So saying that you have a solution of that means there is one deformation that turns mu 0 to 0.
Okay, curve the infinity deformation. You mean a curve the infinity deformation. Yes. So this is correct. My emphasis was on curved versus uncurved. So currently the goal is to turn this curved category into an uncurved category. But indeed, if we just had an infinity category and one of these objects, it would deform.
And is it obvious that it turns from 0 to 0?
Is it
Yeah.
But I didn't even define for you the differential.
I mean, I'm also asking, Simon was talking about very similar things last week.
I wasn't here. I don't know what he was talking about, but this is standard. I mean, I'm not talking about some cutting edge new technology. This has been always standard in FOQ.
I mean,
But you're doing DG, right? Is that AFU?
No, I'm looking at trophy algebra. Okay. I mean, I'm doing L instead of A. And very slow. I'm getting rid of the infinity by looking at the Tom Whitney resolution instead of the Shishkin resolution.
but the curvature was a key player also.
Yes. My question is, so B is a bounding quotient. Okay, so bounding quotients are the same as solutions of the Morikawa equations.
Yes.
So I want to list the differential in the language.
Except that we don't have a differential yet.
Yeah,
We're
but
making it into a differential.
Will be M1 plus M2 times E at least.
Again, like I know. Let me just continue because I think I've already spent 35 minutes, and
It's not the most interesting part of the story.
I mean, it's
Maybe.
yeah. Let me just fast forward to the development that allows, again, in the literature, what allows anyone to ever say I computed the Fukaya category as a whole. Okay, so this is it already appeared in Vanstone. So Fukaya categories have a number of structures and properties that lead to the following automatic generation statement. Theorem, automatic generation. And this is a first application is Perot-Sheridan. I'm going to just say the same names as Brent did, and then there's Ganatra and Sanda. So they did this in a situation that's directly kind of related to mirror symmetry. It was kind of just meant to apply to a mirror symmetry situation. And these two people kind of really found what's essential in this argument and made a more general statement that could be made without reference to mirror symmetry. Okay, so I choose to say this. So assume that I have a subcategory. BC and subcategory. Subcategory. Okay, and now the statement is that if A is what's called homologically smooth, then a split generates BCN. Okay, so now there are a number of things to explain here, but so I just barely gave you the definition, and then there's like many years of development, and then there's just this like one statement that turned out to be very important. So kind of the way to read this statement is you look at this Fukaya category, supposedly huge, all the Lagrangians and so on, you find just some subcategory, maybe consisting of just one Lagrangian, so that it satisfies this, so that it's the subcategory with that object satisfies this condition, then you know that it actually captures all of the Fukaya category. Okay, and here there's something, this split generates. Okay, so this is important. So when you say you could, for example, when you're trying to compute a chain complex, you don't ever like actually compute the chain complex, right? What it really means is that you compute its homology in some kind of robust way. So you can think of this split generates as we're not really computing this Fuk, but we're computing some algebraic thing that's derived from Fuk. So derived category, I'll say something a bit more, but this was another thing I think that was initially motivated from mirror symmetry, that you should like do something before you can, like there is some natural operation that you can do to the Fukaya category, and after that you could actually compute it in full. I think this was also mirror symmetry. Like if you just didn't have mirror symmetry and just made this definition, I don't know if you would expect this. Okay, so let me not define the homologically smooth, but tell you when it holds in the cases that are relevant to mirror symmetry. So I will look at the B side, and so Y, a scheme, algebraic variety, and I think this is true. So then a DG enhancement, so just the derived category of coherent sheaves, if you don't know what this is, satisfies this property. Always.
A smooth scheme.
No, so I think derived category because you can always resolve the diagonal by coherent sheaves. The issue is to resolve, so that's a statement about perf. The thing that's smooth, if and only if the category is smooth, is the perf. So, mirror symmetry tells us something like a Fukaya category should be isomorphic to this. So we can presumably first find this coherent category inside the Fukaya category. And then it automatically is the entire Fukaya category because of this result. Okay, so now this really reduces the number of work that you have to do. And then also, moreover,
But if you take a closed subscheme,
Perf.
is that also something homologically smooth?
it's not. This is a categorical property. It's not about a subscheme. It's about a category.
Yeah, but corresponding category.
You can just take that as your variety and make the statement about that.
But it's not a subcategory, then you have a subscheme.
But I'm not saying anything about a subcategory of the derived category of coherent sheaves. I'm saying a subcategory of Fukaya categories.
The question, as I understand it, is if I take a subscheme of Y and look at the co-DG of this thing, is this?
But why is it important that it's a subvariety?
I mean, you could go to a point and then the co-DG of a point would generate co-DG Y for every Y.
Yes, that's the question.
Called DG of a point, but I don't know. I don't know. I don't know what this means. So I'm making one statement about generating Fukaya categories.
Yeah, because
Okay.
we're using additional information about the bounded cochain Fukaya category.
Yeah, this is a statement that's, as I said, it has some extra structures that make this true. This is not a general statement about a infinity category.
Hold for subcategories of co-DG.
Huh?
Yeah, automatic generation does not hold.
No, it does not hold. As far as I know, maybe there are some statements, but as far as I know, there is no such statement. This is really something that's specific to Fukaya categories. Because Fukaya category is not just open, like if you have a symplectic manifold, you also have this entire closed string package, and the closed string and open string package interact. It's much richer than just an infinity category. So you use all of that to prove this statement. First Y is homologically smooth if and only if Y is smooth. So these are the sheaves which are locally, Zariski locally, just have resolutions by finite resolutions by free sheaves. Just some of these guys. Or to the end, the structure sheaf. It can be built by kind of taking cones over the structure sheaf. Locally, not globally. That's what perf means.
Can you repeat?
Can I repeat? Yes. So these perf is a subcategory of this code. So the kind of coherent sheaves that I consider are the ones which have locally resolutions by free sheaves.
Finite.
Finite resolutions. Yes, it's important that it's finite.
And it's known how to enrich or how to modify perf Y so it becomes homologically smoothness and mild singularity.
Again, I mean, it's a good question, and I just can't give you a quick answer. It's a whole field of category of singularities, and there are other people here who can. Okay, so split generates. Oh, I also want to say one more thing without fully explaining. This homological smoothness is a Morita invariant. Concept, so which essentially means that it's captured by this bit, like split. Okay, let me say this. Split generates means split generate means, how am I going to say this quickly? It generates, so it, every, perf A, perf PC, and is quasi-equivalence. So this perf is now, it's a generalization of, so here I apply the perf operation to this DG enhancement of the coherent sheaf category, and then I obtain this. But it can be applied in general. And what it means is you take the closure of this category inside this module category under taking cones and sum ends. Okay, so it's difficult to, you may have seen this as the Karubi completion of the triangulated closure. Another collection of words that don't help if you don't know already what this is. But you can think of it as taking homology. I don't know. That's the best model that I have for it without really defining what it is. It's doing something to the category to make it simpler. And now if you take you can now take the cohomology category of this, and this will be a triangulated category. Idempotent closed triangulated category.
What kind of object is called A?
So it has all the objects inside the module category that can be built by taking cones on objects of A, and then taking sum ends.
Is it a triangulated category?
So it's triangulated and idempotent closed. It's the smallest category that has those properties and contains A.
Infinity category.
Okay, but like I know, yes, it's an infinity category. I know your questions are valid. It's just I can't like. It's a book to explain this. Okay, so it's something, you know, it's something. It's a generalization of that. Okay, so and Morita invariant means that like it's already captured. It's captured. This is a property that's captured by the perf of the category. So if you have two A and B whose perfs are quasi-equivalent, then if one is homologically smooth, the other will also be homologically smooth.
I think I still had a question for
Yes.
DG category of cohesion is homological.
Yes.
How if Y is not smooth, how does one guarantee that the resolution is bounded?
Because it's a coherent sheet itself already. The diagonal is a coherent sheet itself.
Okay, you allow. Oh, yeah, okay, that's true. Okay.
So it has a resolution of length 1. So I'm saying that triviality. I'm just saying it's already resolved. Okay, so I can now say what a homological mirror symmetry at least says. So I say that Y scheme over a Novikov field satisfies HMS if the H0 of this perf of Fuk DCM is the dB co of Y. Okay, this is what proving homological mirror symmetry means. Okay, so I didn't so I told you in words, but like this Novikov field is used to, if you have something like this, you count it. You don't say you don't count it by 1. You count it by the U. Let's say you count it by its symplectic area. Okay, so that's how T is used.
Do you need to match the moduli compared to moduli?
Again, I just like really indicated that I say that. Okay.
Yeah, the right hand side is not anywhere. There's no buffering on the right hand side.
There is, it's a scheme over lambda.
Oh, lambda, sorry, it is. Sure, that's fine.
Okay, so now I need to say this, and it will end my talk. I don't know how.
Use two notations, Koch DG and DG Koch.
So this is a DG enhancement of the derived category of coherent sheaves, and this is just the derived category. So it's the H0. Huh?
So sorry, given.
So I mean, it's the H0 of the K. You do the whole thing, right? You take the you need to take complexes and so on, right? So you have coherent sheaves, and then you consider complexes of coherent sheaves, and that's the thing that's a DG, triangulated DG category, and then you take the H0 of that. So, yeah. Not just the H0. Yeah, I think you understand. I think you know. Yes.
Maybe you said it here, but I didn't listen to it. Is given Y, is M uniquely determined, or there is some? So you say the statement says given Y, a scheme over the Novikov ring satisfies homological mirror symmetry if there exists M such that this is true.
No,
or?
I already have M.
Ah.
I've been talking about M, so M is I have.
So you fix M.
Yes.
And then you say that
For
Y
M,
satisfies
let's say
HMS
for M. Let's write for M.
So there might be several Ys that satisfy the.
There might be several ways.
And they satisfy some relation between them, or.
Okay, like these are all very good research directions. Like the people write like series of papers, great, but I can't tell you the answer. Yes, it's possible.
This is a good answer.
Yeah,
these
it's
people
like
think about this.
there are, yes, this is a big field. Okay, there is a variant of Fuk M that allows one to work over a discretely valued field. So I'll write DVR, but something like this: K double bracket Q1 Qn, just this complete DVR instead of the Novikov field, which is not Noetherian, kind of algebraically bad. This guy is algebraically better, but also avoids a lot of technical difficulties. So this is the relative Fukaya category. Category of Perot and Sheridan, but it was also, I mean, the ideas mostly due to Seidel, I think. Okay, so for this relative Fukaya category, we have M, but we also have another piece of data, which is an ample divisor. So it's going to be the Fukaya category of M relative to this divisor. Okay, so let me just write again, it's a symplectic definition. Well, I will say the symplectic version of the definition. So this is, so each of these DIs are just symplectic submanifolds.
What is the discrete valuation? There are many variables.
Yes. Awesome. So what are those Qs? Those are free variables?
Let me just.
There is some completely.
So it's completed with respect to the maximal ideal. I don't know. Standard, I think.
Yeah, but it has dimension, not one. Maybe.
DBI is mention one usually.
Okay, sorry. So I used the wrong word. So it just means let's just take it to be this way.
Complete local.
Yeah, complete local. Okay, great. I just meant like it doesn't have this accumulation of valuations. That's what like it's this. Okay. Anyways, let's continue. Let's continue. So okay, I have this this divisor inside M, and by divisor I mean some codimension 2 symplectic submanifolds which intersect transversely, but they also have to satisfy an extra assumption that makes them into a symplectic normal crossings divisor. Okay, to see what this assumption is, you can read this Tehrani-Zinger. So it's not just, they're symplectically orthogonal, but that's not enough. Symplectic divisors are a little bit more complicated than complex. Well, not complicated, but it's too flexible, so you have to make it less flexible. So D is something like that, but it's also supposed to be ample. And that will mean, for me, something like this. There exists some positive numbers such that the symplectic class is equal to, and the I, Poincare dual di. Okay, so you can really think of a situation where you have a Kähler manifold, a projective, complex projective variety, and an SNC divisor, which supports an ample divisor.
And this theory, subjecting our crossing divisors, is related with the papers with also Tehrani and
I can add McLean to it. So it started with Tehrani-Zinger, and then McLean joined the group.
Is a theory of regularizations.
Yes. But I'm just citing it so that I don't write a definition here. There is a definition. Okay, so I'm not using any complicated thing about what they did. At least at this point. Okay. So then M minus D admits a Liouville structure. This means that there is a theta of one form in this complement that is a primitive of omega, and we'll say with positive residues around the i's and some properties that I'm not writing. Okay, so the picture is something like this. So you have like M, you have D, and then in the complement of D, you have this Liouville structure, and I'm indicating the Liouville vector field. So there's a skeleton here. Okay?
Is this a proposition?
Positive.
So this blackboard is a proposition.
Yeah. It's something that you need to prove. Again, I can cite something, so this is in McLean's papers. Okay, so then
Are we holomorphic here, or is it?
Huh?
Is there some real form, or is it holomorphic?
There's nothing holomorphic in the data. It's just a symplectic manifold. Everything is C infinity. I just gave you an example of this. If you have a Kähler manifold and you have an SNC divisor which supports an ample divisor, that will give you an example of it. Okay? Okay, so now MD is also a curved category. Curved infinity category. And now the objects are graded, oriented, spin, the same stuff, but in addition, exact, theta exact Lagrangians. Okay. Huh? Yeah, they're contained in the complement. Thank you. Contained in M minus D.
There are some behavior. How they go.
No, there is no behavior because they're compacted. They just don't interact with D.
What does spin mean?
Okay, let me skip this. It's something about signs. To count with signs, you need to have extra data. It's the same
Okay,
story.
so like grading.
Huh? Grading is this one. That's another. Yeah. So morphisms are really the same. Same. Okay. And the real kind of difference happens in structure maps. And the only difference in structure maps is the weight. Okay, I used to weigh these structure maps, the curves that contribute to these structure maps by their symplectic area. Now I will weigh them by their intersection number with the divisor. Okay, so now weight Floer solutions by the intersection number. D. Okay. Oh, let's make these integers, I guess. Well, no. Yeah, let's make them integers. Integers. I mean, it's not, no. Sorry, I take that back. I don't, let me make a really correct statement. Sorry. I just weigh them by their intersections. So nothing about omega is used in this, but there is a way to recover, at least for these particular objects, the Fukaya category with these objects from these counts by making a base change. So I'll make two statements. One is that consider this Fuk MD tensor with K. So over this K Q1 Qn. Okay, so I'm just setting all of these variables to 0. Okay. This thing is just the Fukaya category, compact Fukaya category of the complement. I'm only considering Lagrangians which live in the complement, are exact, compact, and now they're just not allowed to interact with D at all.
So here, those solutions are allowed to be in the whole M.
Yes, yes. Here, everything's happening everywhere in M. Here, it's happening in M minus D. So setting all of these formal variables to 0 has that effect. Okay? And two, so this is actually not, this is a non-trivial statement. This is a positivity of intersection. And this positivity of intersection becomes a little bit tricky because you can have curves that intersect the divisor positively, which you can then add to them negative curves that live on the divisor and make them actually have zero intersection while zero homological intersection while geometrically intersecting the divisor. So they have to work really hard to, not really hard, but they have to come up with ideas to resolve this issue. But they can do it. So it's a bit more complicated than what I wrote. Okay. The second statement that I want to make is there is a map from this K to N to the Novikov field, which sends Qi to T to the lambda I think. Okay, such that if you base change this Fuk MD, tensor. Okay, it would be really good if I gave a name to this string, but it did not. Then this thing is isomorphic to. So let me not say it like that again. There's a map, book M, which is a full embedding. Full, faithful. Okay, so I can recover. Yes, I'm done. I will. I mean, I'm not done, but I will finish. Yeah, from this relative Fukaya category, you can recover the usual Fukaya category, except you have some limitational objects. The objects are still the ones. So without doing anything more, you can only capture the objects here, which are like still disjoint from D and the exact and the complement and so on. But again, because we have this automatic generation results, if we prove homological mirror symmetry for this, then we will get it for this by this automatic generation results. Okay, I'm done. Sorry.